All right, we're going to get started here. My name is Garrett Brewer. I'm a Course 3 alum at MIT. I'll be emceeing the event this evening. Joining us this evening is Professor Gerbrand Ceder, the MIT R.P. Simmons Professor of Materials Science and Engineering. Gerrit is a metallurgist by training who became interested in the fundamentals of materials in the late 80s. He obtained his engineering degree in metallurgy and materials science from the Catholic University of Leuven, Belgium in 1988. Crossing an ocean and a continent, he moved just across the bay from here to obtain his Ph.D. from the University of California, Berkeley, 3 years later in 1991. So he's no stranger to the great weather that we have here in the Bay. Gerrit's first personal interaction with MIT came when a friend suggested that he check out a cool job opportunity at a school called MIT. Thinking that it might be a temporary gig, probably because he liked the West Coast weather so much, he applied and was accepted. 23 years later, Gerrit still finds himself at MIT, now a professor, and loving it. He enjoys the position where one day you can be doing quantum mechanics and the next you can be starting a company. In 2006, Professor Ceder began the Materials Genome Project, which as of May has tens of thousands of compounds in the database and is used by more than 5,000 researchers, as he's just explained this evening. The Materials Genome Project incorporates first principles computations, whereby the properties of materials are predicted from basic physics. Applications of this project include high-temperature superconductors, electrodes for rechargeable batteries, and even the carbon composite body on the new BMW 3i series electric car. So Tesla, watch out. Professor Ceder's work has even made it onto the campaign trail, with Obama discussing Professor Ceder's efforts as part of a White House science initiative. Please join me in welcoming Professor Gerrit Ceder.
Okay, do we switch this over? Or? Here we go. Okay. Well, thank you all for hosting this. It's wonderful to be here among, I know a lot of you are alumni and friends of MIT, and the others are welcome too. I want to talk a little about, in general, the work that I do and how that led to the materials genome, but I want to put that in a bit of perspective. I want to start with this song. Some of you older people may know this song, right? Okay, so 1973, what happened in 1973? This was actually a hit in 1973, right? But other things happened in 1973. We had the oil crisis in 1973. And, you know, most people forget the oil crisis had nothing to do with shortage of oil, right? It was all political maneuvering. You know, this was Egypt retaliating against Israel, pushing them back out of the Sinai Desert. And essentially, they turned off the tap. And, you know, what happened, right? What happened is that we now import a lot less oil from the Middle East, right? They should have, you'll see that people should have learned from that. This was, in some sense, an early use of manipulation of resources for political gain. You know, you see this more, right? I couldn't find a song for September 7, 2010, but I don't know if you remember what happened that day. That day, Japan arrested a Chinese boat captain. Japan and China, you know, China has many territorial disputes in the ocean, in the sea around China, and this is one of them. And I think you know what followed, right? Within 2 weeks, China blocked shipment of all rare earths to Japan. Guess what happened to the captain? The captain went home 2 days later, right? So again, sort of political use of resource. And why was Japan so afraid, right? You know, rare earths are critical in high tech. You know, you use them in permanent magnets. You use them in, you know, the motors, the generators that go in wind turbines. You use them in optical fiber. You still use them in the older nickel metal hydride batteries. You use them as phosphors to color balance energy savings, right? So they really have sort of critical use and were not trivial to replace. And this led to an enormous sort of flurry of activities, you know. This thing happened only 3 years ago. We now have a critical hub in this country on rare earths. There are new mines that have opened. There are new initiatives all over the world in either mining rare earths, replacing them, or refining them in better ways. So an extremely rapid response because we are so sensitive to this supply. You know, I am a materials scientist, so I have to give you this spiel for materials, right? Today, we see that materials are not just stuff you build stuff from. They really have leveraged value. I think PV is a good example of that, right? Today, the cost of PV is pretty much largely the cost of making panels, installing them, the inverter, everything but the active material, right? So the active material is a small part of the cost of PV. And so what that means is that if you could find an active material with higher efficiency, if you could go from 20 to 30, right, you can actually now amortize your other costs, your installation cost, your panel making cost, your inverter, over actually, over actually less material. So if you have a PV material that's 50% more efficient, you have to make essentially 50% less panels. And that's how you get your leveraged value out of materials. We see the same in batteries, and I think this is underappreciated. If you look at the cost of lithium-ion today, it is largely the cost of making cells and all the crap you have to put in cells. And so what that means is if I can put higher energy density materials in a cell, I get a cell with higher energy content, but it'll be roughly the same cost. And so my cost per kilowatt hour will actually be lower. And so energy density in batteries is actually mainly there to do cost reduction, right? And this is why, for example, startups, like unfortunately one from MIT that worked with low energy density material had actually no chance from the start. Because they had such a low energy density material that you could not scale away the rest of your cost, and which is why high energy density is so important. We see materials for military supremacy. I like the example of the stealth bomber, right? This was an amazing materials technology. There were shape factors, right? Stealth is all about either radar absorption or deflection or transmission, right? And so there was a lot of shape factor to it, but there's a lot of areas where you have high structural components that you actually really will get radar reflection. But so there, people invented dielectric materials for the airframe where you really had to use high-strength steels. They are actually now coated with radar-absorbing ferrofluidic paints. These are sort of fascinating high-tech paints. They really contain small iron particles in them, which are actually organized as they dry in a magnetic field to get the right sort of distance between them and absorption. The part that was the hardest to get rid of was the cockpit, because the pilot needs to see, and so radar goes through the cockpit window and reflects of all the instruments there, and so the cockpit is coated with transparent conductors which absorb the radar. So this was a lot of materials technology that went in stealth. What's interesting about this, so one of these went down in wartime activities, 1999 in Kosovo. And guess what happened? Within a day, Chinese and Russian prospectors were on the side to buy parts. And so that's believed that that's how China got hold of stealth technology. They basically bought parts and just basically reverse engineered them. They looked at everything that was sort of on them. We see this again in other things. If you read the book of General McCaffrey, he claimed that in Desert Storm, night vision was the greatest technological advance they had. Everything was done at night. They had night vision, which is essentially advanced optics, right? With high signal-to-noise ratio, and had such a strategic advantage. Today, most of our competitors and our foes have night vision technology as well. So what is the next thing, right? What do you do if they can see you in the night? You try to do cloaking, right? So cloaking is the next thing in stealth, and it really is not as far as we think. It's almost frightening, but Harry Potter was maybe not that far off. This is actually active cloaking, which is probably not that interesting, which was demonstrated a few years ago in Japan. This is essentially kind of a technology where you take the image from behind and you project it on the front. But today we can cloak in the infrared. In the infrared, you can actually make objects with metamaterials that essentially make infrared light go around it. We cannot do this today in the visible light. But for infrared signals, we can essentially make objects invisible. And so, again, this is largely an advance through materials technology, through the advances in metamaterials. I know there are venture capitalists here and investors in the audience, and materials is not for the faint of heart, right? It is a technology that takes a long time to go to market. Tom Eager from our department did a study quite a long time ago, found that the average was about 18 years. 18 years from when you sort of like get proof of concept in the lab, which is hard to define, to when you have significant commercialization. And not all of that has to do with materials development. Some of it is consumer acceptance issues and testing in the market. But a part of this is because we don't know early on how well materials behave, and we tend to find a lot of problems when we actually field deploy. And so the more we could know about materials ahead of time, the shorter we could make this time, because nobody will invest in this, right? There's a reason that it's mainly big companies who do materials development, because if you tell your investor it's going to take me 18 years to commercialize this material, they'll say goodbye, right? They'll discount you and make it 36 and say goodbye, right? So how are materials invented? Well, I want to remind you how Edison did it, right? We call something in science Edisonian for a reason. Edison, when he was trying to make the light bulb filament, looked at about 3,000 materials. They were all carbonaceous materials. He literally sent out people to the far end of the planet to collect different sources of carbon. And he ultimately settled on a sort of carbon derived from bamboo. But he did all this experimental work, and the sad thing is he didn't actually find the right one, right? Within 15, 20 years, carbon was replaced by tungsten, the tungsten filament. People had figured out, if you do the tungsten in vacuum, it's not going to oxidize and therefore not evaporate, and bam, carbon was gone. So all this work and didn't even find the right one. So how do you really want to do materials design? I want to show you a fragment of a movie. This is how I would like to do materials design. I have to figure out, hold on, I have to find out a way to make this play, which is always hard. Okay, I'm going to get this out of presentation mode and play it like this.
Periodic.
Oh, come on. There we go.
Periodic table. Right here.
Rendering periodic table, sir.
This is our saga last leave us.
485 simulations.
Let's try cerium and dysprosium.
Let's try cerium and dysprosium, just like that, right?
At least it's got to work. Empty shell. Initiate.
Initial biological compatibility appears promising.
He tests biocompatibility right there, right? So this takes us, what, 5 years, 10 years, and then you need FDA approval. So this is how we would like to do it, right? Throw some elements together, see what they do. There are other good scenes. There must be a material scientist on staff. There are other good material scenes in that movie, if you'd like to look at it. But really what we'd like to do is in the information age, when I ask like a 16-year-old, how do you find a good battery material, what do you think they're going to do, right? Yeah, there you go. And that doesn't quite work, right? And then you spend $250,000 and send them to college, right? And you get them a chemistry degree or a material science degree. And now to get a little smarter, they don't Google better battery material, right? They know properties of materials. So what do they do now? They Google properties, right? They go like, oh, I need this voltage, I need good stability, I need good lithium ability. But unfortunately, you can't find that either, right? There is no Google of materials properties. Let me tell you how little we know about the world of materials, or the world of compounds. And I'm limiting myself here to the world of inorganic chemistry. You can do this analysis for organic chemistry as well. But there are about 50,000 to 200,000 known inorganic compounds in the world. That's the ones we know that we have sort of at some point made and looked at in detail. And there may be 50,000 more that we don't know, or 100,000 more. It is actually not a combinatorial explosion. That's a sort of different talk that we could talk about at some point. So the problem is kind of 10 to the 5th, right? 10 to the 5th, maybe 10 to the 6th. That's the size of the problem. I can tell you that today, we sometimes compute materials 10,000 at a time. So we are in this sort of batch size where we are starting to approach taking big chunks out of nature and figuring out how it works. But let me tell you how little we know about these. if you take average materials properties, like the tensor of elastic constants, not just like the elastic modulus, the full tensor, we know that for 200 compounds out of that 100,000. That's it. That's it. You know what the property is that's best known is the superconductivity transition temperature, because so many people were looking for gold, right? In the heydays of superconductivity, people were making everything and measuring TC for it. We know that for about 1,000 materials. The dielectric constant tensor we know for about 300 to 400 materials. You could do this analysis for the band gap, which is important in optical properties. We know that for a few hundred materials. The rest we actually don't know. And before you argue with me that maybe the other materials are not so important, I have a whole set of slides on materials that we failed to discover for 20, 30 years, even though the materials were known because we didn't know what properties they have. Actually, several battery materials were in that category. The materials were known for a long time, and we had sort of no idea that they would be decent battery materials because we just didn't know their properties. So we're actually below 1% in coverage in every sort of real property. So we know nothing, right? So imagine a world where that's different, right? Imagine a world where you're a materials designer and you know all the basic properties of materials. You may know the band gap, right? You may know the effective masses, which will tell you how fast electrons move and what the conductivity can be. You know the Seebeck coefficient, which would tell you what the thermoelectric power is on material. If you're more in deformation, you may want to know what the elastic constants are. If you're into sort of optical phenomena and dielectric phenomena, you may want to know what the absorption spectrum and the dielectric constants are. Again, we don't know these things, right? You may want to know what the point defects are. Very important in processing. Solubilities of other materials. You know, stacking fold energies, Perel's barrier. If you studied any materials, all sort of very basic things. We actually don't know these for all these materials. You may want to know what surface energies are to see what reactivity is with other environments. And imagine that you had the capability to actually query these on demand, that you had a materials idea, you don't know these properties, but tomorrow you can actually get them. The interesting thing is that there is not a single property on this slide that somebody has not computed at some point starting from the basic laws of physics, and it actually works. So all these things actually have been done. They have been done by different people in different parts of the world with different techniques, but they have all been done. And if I took all the properties that actually have been calculated from basic physics, the list is much longer. It's just never been put together. And I'll show you later that you need to put all these things together to actually work in a materials design environment. So how it is done? Well, what we have found, you know, us sort of modeling people, right, is after sort of 30 years of messing around, that in the end, what actually works best is going back to the very fundamental equations of physics. And the reason is there you don't sort of need an experimental fitting, right? You take the Schrödinger equation of physics, we have big enough computers and approximate algorithms that we can solve this, not exactly, but reasonably exactly, right? And sometimes good enough, as I say, usually to make decisions on. You actually don't always need numbers right? You need information so you can make decisions. And so we can do that, and we can simulate materials. You know, here's an ionic conductor where we actually, this is actually a quantum mechanical simulation of the ions moving. This is a fast lithium-ion conductor, and I'll talk a little more about that later for solid-state electrolytes. Once you can compute things, right, that is a milestone. And the reason is computing is one of the most scalable things in the universe, right? Experiments are hard to scale. You need more people, or you need more robots, you need more space, you need more this, you need more that. Computing you can scale, right? So if I can compute once, I can compute twice, I can compute 3 times, I can compute n, right, as a good physicist. And n goes to infinity. You know, to put this in perspective, if you took NERSC, one of the big NERSC is the DOE supercomputing center that's up here in Berkeley. It's actually in Oakland, but about to move. You know, if you got that machine just for a day, right, you can actually calculate basic properties of 20,000 compounds in one day. Now, we don't get it for a day because you actually have to share it with a lot of other people because DOE owns it and so. But just to put this in perspective, this is not a problem of computing time per se. This is more a problem of management of algorithms and stuff like that. There is more than enough computing time in the world to do this, plenty actually over. So you can do this. So that was the vision of the Materials Project and the Materials Genome Project. The vision we had a few years ago at MIT was that we actually could compute what we call the basic properties of materials, and therefore the genes, and disseminate that to the larger materials research and materials design community. So not necessarily for us to do design with, but for other people to work with. You know, I always describe it a bit like when you put stuff on the internet, right? I'm old enough that I remember when the internet started, And people had all these crazy ideas about what people were going to do with it, and most of them were wrong, right? And I think it's when you create a capability like that, you cannot imagine what people will do with it. And we are already starting to see that. By putting this sort of basic information out, people are building more complicated property models. You know, some people are working on corrosion with it, which is, I know nothing about it. So some people are working on transparent conductors, again, which was not a real topic of mine, but they take this kind of information and work with it. So that was the vision of the Materials Genome Project. Today, the Materials Project, I'll tell you later why we dropped the genome, it's a good story, is a collaboration between MIT and Lawrence Berkeley Lab, and the director of it, Christian Persson, is sitting in the second row here, and works with several other universities, and this list is actually sort of growing. Some are funded, some are free collaborators to work with us on generating new property data. But I want to give you some history because it's a good story how this started. This was actually not funded by the federal government early on. The history is that in 2005, I was actually approached by a vice president of research of Duracell, which is owned by Procter & Gamble. And the vice president was sort of good in science, but not very good. And that's sort of the right level, right, for your vice president. Because if they know too much, then everything is impossible. And so she came to me at some point, oh, Geert, I hear you do calculations on battery materials. And she goes, could you calculate everything, like, so we know if there's anything good out there? And this is when you sort of swallow and you go like, yeah, that'll be $1 million in 15 months. And we had no idea how to do it, right? At that time, we had no clue at all what to do it. And we could have just as well said, no, that seems like really complicated. Let me just go back to my office. And so we literally got, we got a band of people together. We decided we couldn't actually run it at MIT. It was way too complicated. So we just hired 5, 6 people and literally worked out of people's apartments and out of my house. And we made them give us the computing. That was the brilliant stroke. So we didn't have to buy any infrastructure. We, for like 12 months, occupied Procter & Gamble's computing center and ran through about 100,000 compounds. The problem was for alkaline batteries. Today, you use manganese dioxide. You essentially need something that can actually undergo multiple reduction steps against the zinc anode, which generates protons. And so they wanted to know, was there something better than manganese dioxide out there? So they could prevent their competitors from doing it. We screened through 130,000 compounds, 30,000 known materials, 100,000 new ones. We found about 1,500 that satisfied all the kind of energy criteria. But what we actually found is that when you looked at the stability problem, so this is in alkaline electrolyte, and it's called an alkaline battery for something. This is like pH 14, 15. This is like super alkaline. I mean, this is basically KOH with a drop of water in it. That most materials are not stable in that. And so that became like the most stringent screening criteria. And we ended up with about 200 compounds, many of them which actually we are not allowed to talk about, but you can just Google patents by Duracell on new compounds and you'll find some of them. Okay. We followed that. Again, this was all funded by industry. We did a lot of work with Umicore, which is second largest producer of battery cathodes in the world, a lot with Bosch, the automotive supplier. We did a little bit of work with A123 and did a lot of work with, still are doing a lot of work with Samsung in that space now. Today, we have decided that we wanted to take a lot of the things we did and bring them into the public sphere. And so that's how we founded the Materials Project, which is open source access to a lot of the computed data. There's something like 3,000 properties computed over about 35,000 compounds. You can go online and there's a web interface and get that. There's more and more data generated every day and more properties. But what the real sort of scientists do is they actually dig in there. You can get keys to get directly in our database with, there's an API built for it, just like Google has an API to Google Maps and so. And you can actually build locally, like in your company or in your research lab, your models that pulls data from that data set without us ever sort of seeing what you do. So there are 30,000 calculated phase diagrams online. Something we're very proud of. Recently, we put what's called Pourbet diagrams online. So Pourbet diagrams are essentially phase diagrams of materials in aqueous environment. So as a function of pH and potential. So they're very important for corrosion. They're important for precipitation reactions out of solution. And Pourbet had those worked for like 10 years to just do them on the elements. So he has like 100 in his book. We, by computationally scaling them, have now over 1 million diagrams of pretty much any material you can imagine. We have now the phase diagram of how it behaves in aqueous environment in the Materials Project. And this went online, I think about a month ago, right? So proof of concept, there have been materials made with this, actually. I showed you the alkaline battery one. The middle one is one out of my own field on a novel class of lithium-ion electrodes. These are carbonophosphates, which is a highly unusual chemistry. We were trying to combine carbonate groups with phosphate groups for sort of safety issues that I don't want to go into right now. And very recently, a paper came out on p-type transparent conductors, which is a big deal, right? It's easy to make n-type transparent conductors, but in many devices, you need a p-type transparent conductor. And there are not many choices, and that paper shows how you computationally identified several p-type. And some of them have been made now. Okay, then something special happened, and we got a call from the White House at one point, not from the White House, from people in the White House. And they said, we've heard about this materials genome thing, like this genome thing. And that sounds really cool. I think they were mainly interested in the name. And so we want to start a materials genome initiative. And there was a bit of talking back and forth, and that's how the National Materials Genome Initiative got started, which is really more general about a renaissance of manufacturing, but there's sort of one of the thrusts in there is computational materials design, and it's been a very big piece of the materials genome. The deal was, I was going to tell you the story, that they would only launch the national initiative under this name if we dropped the name, because otherwise there would be too much confusion. So there were lawyers went at work, and we have an agreement. We can use the Materials Project, a genomic initiative, but not the Materials Genome Project. I think I'm being recorded, right? Okay, so that's the story. So I want to talk a little bit sort of about the impact and things we do with this. This is mainly out of my own field. I do a lot of materials design, but like 80% of it is in the battery space. So I'm going to give you some examples of things I do in that area. But first I want to sort of give you a few dangerous slides, sort of my vision on EVs, and I know this is a dangerous part of the country to do this. There probably are people who own EVs and people who even make them in the audience. So I think that I used to be a serious skeptic about EVs, and I'll show you where that came from. And I am still a skeptic in terms of large-scale penetration. But that does not mean it is not a viable technology, and I think it is a viable technology for many companies already. You don't need to own 50% of the market to have a viable product. And I think this is a kind of technology that will grow. It is here to stay, that I am convinced of. It just won't grow as fast as people tend to claim sometimes. So here's my story of EV. The first EV I drove was this one. This was in Paris. This is an EV made by, what's her name? She's a fashion designer. She was the one, God, what is her name again? She did the miniskirts in the 1960s. I'm trying to remember her name, but it'll come back to me. And her hobby now is making EVs. So she has people who design this for her, and this is the space age thing. I drove this on the Champs-Élysées. It has no suspension, which is really painful. And it started raining, and it has no wipers, because this bubble, you can't put wipers on this thing, right? So that was my first EV. After that, we had ugly. We had funny. And I know I'm going to insult a lot of people in the audience. We had boring, right? And these were all great technologies, but we had kind of slow. We had great but expensive, right? But I think what is happening, if you sort of take the intersection of this, interesting things are happening, right? In my opinion, what Tesla did very right, is that there are very few automotive innovations that we try to start from the bottom of the market. This is unusual, right? When we invent something in automotive, we start at the top of the market, right? Airbags, cruise control, anti-lock brakes, because there you can make money, right? And you have margin. And then you push it down. What all these other people try to do is start from the bottom of the market, which is really a terrible mistake to make, right? You don't have margins there, and you don't have a clientele that can pay a lot of money. The other thing that Tesla did right is that, you can market EVs for multiple things, right? There's the environmental benefit, right? You know, I have a Prius, right? And you know why most people bought a Prius? Because it says Prius on it, right? Hybrid. I mean, that badge was worth all the money. I mean, it's a fine car, but because it looked different. You know, is that the Boston Red Sox, or is that the Red Sox winning the World Series? No. Okay. Oh yeah, there you go. You know, so marketing and branding was actually very important, but an aspect that was neglected, I think, by these car makers was that electrical motors give you very high performance, right? And that's what Tesla did in the upper end of the market segment. I mean, we all knew this, but they actually demonstrated it and showed that you could not only have sort of a funky environmental car, but you can do it high performance. Now, the question is, can you do it sort of at a lower price point? And I'll talk a little bit about it. And I think that market segment has arrived. I think the hybrid here has arrived. You look at something that BMW does with the i3, right? The i3 is not on the market yet in California. This is an attractive car. It's in the sort of $40,000, $45,000 segment, right? Which means it's approachable by a lot more of us. It does 0 to 60 in 7 seconds. I haven't test driven it, at least that's what they say. It's a very well-engineered car. It's, you know, sort of BMW engineered car. It looks nicer than some of these other ones in there. And it's, I'll show you a little bit. It's amazing engineering done on it, right? They've gone for the lower range, and I'll talk a little bit about it. They've sort of done the 100-mile range, which is where a lot of EVs have positioned themselves, right? 180 miles with range extender, that's sort of irrelevant. With range extender, it's pretty much whatever you want to go if you can find gas, right? But really interesting materials innovation, carbon fiber body, which has allowed for weight reduction in the car, almost to compensate for the battery. They got about 200-300 kilograms. It's a sort of space body because they don't need pillars on the doors. And you know, interesting, BMW claims, and I found this first hard to believe, that the carbon fiber body is actually cheaper than the steel body, which, you know, it's hard to believe, but they have made this statement publicly that they can actually make it with less infrastructure cost. They have done a lot of research on carbon fiber manufacturing. They've done a lot of innovation on the drying times and things like that. They can actually move things much faster through production than we could do in the older days in carbon fiber technology. So I think there is somebody from Tesla here, so this may be something for Tesla to watch out for. So I want to talk a little bit about sort of remaining battery issues, because there are remaining issues. Batteries need to, and in my opinion, there are only 3 of them. And the other ones sort of feed into them. There's cost, safety, and power. The reason, you know, I don't bring up energy density because in my opinion, energy density largely feeds into the cost. If you increase the energy density, you reduce the cost. And cost is basically what sets range, right? If you want to spend more, if you have more money, you buy a bigger battery and you have more range. It's somewhat of a simplification, but it's largely a range issue. So here's my math. This is largely borne out by the cars. You see, if you have a fairly smallish car or a well-engineered, light-weighted car, you get about 4 miles driving per kilowatt hour, roughly, right? So if you want 200 miles, which I think is a kind of minimal range for large-scale customer acceptance, you need about a 50 kilowatt hour battery pack. And that's borne out, right? You look at sort of what Tesla comes out with. You look at the guys who have 100 miles, they have a half the size of that battery pack. They have about 20-ish kilowatt hour. So if your battery pack is $500 a kilowatt hour, you're spending about $25,000 on the battery pack. If you go down to the long-term DOE targets of $250, you're spending about $12,000 on the battery pack. So it's a big chunk of the cost of the car, and now you still have to build the car around it, right? And now you see why this is so hard to do on very sort of small cars, on a car that you want to sell for $20,000. It's really hard to do. So battery pricing has to come down. It's somewhere in the $400 to $1,000, although, again, Tesla probably has the better model where, because they buy commodity cells, they probably sit a bit below that actually right now. If you do a large car, right, if you want to drive the giant SUV, these numbers are not going to look as good, right? If you took a car from today, right, that you not too much care in the aerodynamics, in the weight, you're probably going to get only about 2 miles per kilowatt hour. So now the math looks bad, right? If you want that 200 miles driving range, your battery cost is sort of $25,000 to $50,000, right? So cost is range, right? It's really that simple. So as I said, best way to get cost down is to get higher energy density material, because you kill all your overhead, right? You always need to buy your current collectors in the cell, your electrolyte, your salts, you know, your separator. All these costs are fixed in the cell. If you can put in higher energy density material, you get more energy for the same fixed cost. The question is, do large battery packs make sense? And I hope this may lead to a heated debate, right? Because I think there are quite differences of opinion. So this is a graph of American driving patterns. It's a cumulative histogram. It takes a bit of explanation. Essentially what it measures is, if I take up all the days that you drive a certain mileage, like 30 miles or less, how much of your total driving is that in a year, right? So if I take all the days you drive 20 miles or less, that's actually 50% of all your driving. If I take all the days you drive 40 miles or less, that's 2/3 of all your driving. And this is kind of what we know intuitively, right? Most of the time, you drive not a lot in a day, right? But once in a while, you want to take a long trip and you want to go somewhere. And so this is the argument that's made that, well, if you did electric drive on a short distance, right? If you could build 40-mile electric drive, you could displace 2/3 of all gasoline use, right? But of course, you need something else than to go the extra mile, as they say, right? And so this is the argument that's made for plug-in HEV, or as it's called, the V plus range extender. So the idea is get a smaller battery, because the battery is your big capital cost, and build a small range extender, which, you know, in the Volt was actually a fairly big engine. But if you look at what the BMW does, it's actually a very small, almost scooter-like engine, which just generates electricity. And it's like I think you have like a 9-liter tank or something like that for gasoline. There are issues, right? If you have a big battery pack, if you have 100 kilowatt hour, and let's say you want like Sears acceleration, this is like a lot, right? You want 100 kilowatt of power, which is a lot. That's like 130 horsepower or something like that. So in a big battery, that's relatively a low discharge rate. You know, if I get 100 kilowatt out of a 100 kilowatt hour battery pack, that's what's called a 1C rate. If I get that out of a 20 kilowatt hour battery, if I get that out of my leaf, right? If I want to get 100 kilowatt power out of my leaf, that's an enormous discharge rate compared to the pack. So that's the counter argument, that if you make the battery pack smaller, you need to get relatively high power rates, which means you're taxing the battery also higher. Power we kind of know how to engineer, though. You know, a while ago I did work on lithium iron phosphate to sort of demonstrate that power capability of batteries is not limited by the materials anymore. It is limited by all the stuff around it. And this was on lithium iron phosphate, where we first showed theoretically that lithium could diffuse super fast in it. And so what happens actually inside the battery when you charge and discharge is lithium flows from one electrode to the other. And in the discharge, it actually just flows to the cathode and actually sort of gets intercalated in the material, and it has to do that by solid-state diffusion. It has to diffuse in there and sort of get stored in there. If you can do that very fast, you can make high-power electrodes. So what we learned to do was essentially engineer the microstructure between particles. What we actually found is that the slope paths were actually the sort of interfacial contacts between particles. So what actually we just put on there, we tried to put a fast ion conductor on there, so that we could very fast lithium-ion conduction through these particles. And we did that sort of through phase diagram engineering. We actually put a amorphous glass, a pyrophosphate glass, which is in that shaded region there, on the particles. And you actually see this here. This is actually a TM picture. This is actually lithium iron phosphate, and this is the intergranular film, which is the fast ion conductor. So you have pathways for fast lithium-ion diffusion along the grain contacts, and then can go rapidly into the grain. And so we established what was at the time the highest charge and discharge rate for any electrode material. These are the C rates here are not temperatures. A C rate is like 10 C means you can do 10 charges or discharges per hour. So 400 C means that you essentially could do, in principle, 400 cycles per hour, which is really what one per like 9 seconds or something like that, right? We now did 1,000 C. You start losing capacity. This is essentially a charge-discharge pulse that charges the electrode about 1/3 of the way in 3 seconds, right? And so what we showed with this is that at the materials level, you are not limited anymore by in charging rate and discharge. There are other limitations, right? You know, the biggest limitation if you buy an electric vehicle in charge rate is your power capability. It's where you plug it in. If you plug it in your wall plug in your house, right, you get what, about 20 amps, at best 110 volts, you get about 2 kilowatts. So if you charge a 20 kilowatt hour battery pack, you're going to need 10 hours, right? And so when you go to really big batteries, it's more an infrastructure problem. That's the issue. Okay, safety. I think that safety will be the thorn that will, on occasion, spike up. And there's a real difference in engineering between Boeing and Tesla here. Boeing, being an aircraft manufacturer using lithium-ion, engineered a battery not to fail. And we all know how that worked, right? This was like, I mean, this was, you look at the specs of that battery pack, this was a disaster. I mean, you know, it was a financial disaster for Boeing too, right? I mean, how many 787s got grounded, and they will have to reimburse the airlines for that. So this is a really expensive battery fire, right? Tesla had another strategy, right? Tesla sort of designs for failure, right? So the whole idea is that a cell can fail and in principle can catch fire and not infect the battery pack. But as we sort of recently saw, so while that is a good strategy, designing for failure is always better, right, than designing not to fail, right? We recently saw that that still has issues, right? That there can be issues that when you have sort of destructive interference with the pack, right, which is really what happened here, that you can have fire. Now, you know, we shouldn't overblow these, right? Fires happen all the time. There are enormous amounts of car fires. But in this industry, of course, all eyes are on it, so it is an issue. The important thing to know about is these are all electrolyte fires in the end. So what happens in a battery is that the electrolyte is an organic solvent because that's pretty much the only electrolytes we have. They have a very high flash point. And so what happens is that there are two ways that a cell essentially can catch fire. If you puncture a cell and the electrolyte leaks out and it sees any spark, right? And remember, you often have high voltage sitting around, right, with the battery pack. It sees any spark, it will set off the electrolyte, and actually the vapor of the electrolyte often, right? The other way it can happen is the cathode material is highly oxidizing when it's charged. And so you basically have an oxidant and a fuel in a package together about 50 micron apart from each other. And so if you heat that up, you basically, you know, it's an explosive, right? That's how you make explosives. You put the oxidant and the reductant together, right? A lot of that can be mitigated. But the problem of sort of electrolyte leaking and spilling fire is a lot harder, right, to deal with. So in my opinion, the only way we were able to completely get rid of this problem, and we're not totally sure this is possible, is by going to non-combustible electrolytes. And the only ones so far that have come close to working are complete solid-state electrolytes. So can you make a solid, an inorganic electrolyte that is a really fast lithium-ion conductor, so you can put it sort of in a battery between the electrodes and make batteries out of? And we thought the answer was no. But 2 years ago, a few groups in Japan kind of proved us wrong. Kayama et al., working with Toyota, showed that this material, which is referred to as LGPS, it's a lithium germanium thiophosphate compound, has really high conductivity for lithium ions. It is actually, at room temperature, as good a conductor as the liquid electrolytes we use today, which is amazing, right? This is a solid through which the ions go as fast as through a liquid. But here's the good news. So the conductivity is the red line. This is a 1/T plot. The activation energy is much lower. So actually, if you go to low temperature, this stuff is actually even better than a liquid electrolyte. And batteries sometimes have issues at low temperature. So this is an amazing material. Now, to make this into batteries, there are all kinds of issues. First of all, you're going to have to totally change the manufacturing industry. Because the way batteries are made today is by coating technology, lamination. This is going to be solid deposition. So I don't know if there's anybody from Applied Materials here. This is your job. There you go. This is your job. You know, this is what you guys are good at. But there are other problems, right? Look at that composition. Germanium. You know what the world production of germanium is? You know, it's like 30 tons or something like that. Or as my friend says, 2 trucks. That's the world production of germanium. And by the way, somebody else will always pay more for it than you if you're in the battery industry, right? You know, the people with infrared detectors, the semiconductor people, they will always outprice you, right? And by the way, there are no germanium mines. It's a byproduct of other things. So you can't you can't fix the supply problem by going to mine more. So real problem. So here's some of the questions we had when this work came out. Is the conductivity real? Is it really one-dimensional? I won't say much about that since it's a bit odd that we thought that couldn't be right. One-dimensional conductors typically never work well. They claimed that you could put 5 volt over this, which is typically what you get in a lithium battery, somewhere between 4 and 5 volt. This is highly surprising in a sulfide. Sulfides usually don't have a large enough band gap. Can sulfur be replaced? That would be great, because sulfides tends to be water sensitive, and so they're more expensive to work with because you have to protect them from moisture. So if you could replace it, that'd be great. And of course, germanium is a non-starter. You will not make batteries with germanium. Toyota demonstrated a little scooter battery, and I don't even want to think how much it cost them, right? It was like... Okay, so we did computations on this and first sort of confirmed the high conductivity, but found that it's a 3-dimensional conductor. And this is really important because a 1-dimensional conductor would have never worked in real life. It's a 3-dimensional conductor, so it conducts in 3 directions, which is really important. You can see that from the simulation. And that's not confirmed by experiments, just a few months ago. I think my battery's dying, typically. But a few other things. Stability, this is really important, right? A battery is an extremely aggressive environment. You're essentially, at one point, at 0 volt, which is where you're roughly metallic lithium-like, and at the other point, you're at 5 volt. And to put that in, if you're a chemist, right, in chemistry terms, that's a 500 kilojoule driving force for a 1 electron reaction. And it's a 1 megajoule driving force for a 2 electron reaction. So basically, almost everything can happen uphill, because you have a megajoule of energy sitting around there if you can move electrons between these two things. So a lot of things break down. That's part of the problem. So to look at actually what happens to this conductor against the anode and cathode, we actually calculate phase diagrams. And what we predicted computation is that this material would not be stable against the electrodes. That's not necessarily bad news. It just means you have to do stuff. So we predict that on the anode, it would decompose in these 3 compounds here. And the problem is this is a metal, and that sends your electrons through the electrolyte, so that's bad news. And on the cathode, it decomposes into these 2. And that has now been confirmed. But that is a solvable problem. And people do that by, just like in the semiconductor industry, by building barrier layers. That's how that's going to be solved. So it's a problem, but it's a manageable problem. Okay. But here's the really important thing. You have to get rid of germanium, number 1, and maybe of sulfur. So this is where computation is great. We are chemistry agnostic, right? For the computers, it's all electrons and nuclei, Higgs particles. Somewhere in there, right? Somewhere in there. So replacing sulfur, we looked at selenium. That was more academic because you really don't want to go to selenium. And oxygen, of course. And germanium, we looked at silicon and tin. So here's what we found. First, we looked at where these materials are stable. This is where sort of this high-throughput computing stuff would come in. And this is a bit technical. So what we actually calculate is, we do all the phase diagram calculations. We literally calculate hundreds of competing phases as possibilities. And we look at what the driving force is to go to other phases. And you want that as low as possible. Ideally, you want that 0. So the material you can make, LGPS, has a 15 milli-electron volt driving force, that's per atom, to go to another material. That's something we know we can manage. Usually, we can keep the material stable. And what you see is that if you keep the sulfide and you replace germanium by silicon or tin, you have about the same number. And that's good news. That means that if you can make the germanium version, which we know you can probably make the other ones. But the bad news is, if I replace the anion by oxygen, that number goes way up. And we predicted that it would not be possible to make the oxides. And that's bad news. Okay, so we got, the glass is half full, right? So we predicted that the silicide and the tin version would be good. They have great conductivity, just as good as LGPS. So we put that out a year after the initial material came out. We put that out in the literature, and you know how the story is going to end, right? So now, just a few weeks ago, just on time for this talk, a group presented that they actually made the material. The tin version of the material has been made of the semiconductor, and look at how the calculation and the experiment agree. So the conductivity is smack on, the activation energy is almost exactly on. So in that sense, it's sort of a real triumph here of computational design. And we're just all waiting for the silicon version, because the silicon version is going to be the really cheap version, right? And it's only a matter of time, in my opinion, before that one is actually going to be having been made. And we may have a really cool solid-state electrolyte for batteries. So here's how we started in 2011 with the experiments out in the literature. Then we computed, we confirmed the conductivity, we predicted 3D pathways instead of 1D. We predicted decomposition, that's been confirmed. We predicted silicon and tin substitute structures, and at least one of them has been made now. So it's an example of really, think about this all happened in less than 2 years, right? And the original material came out August 2011. We're 2 years later, and we essentially already have replacements and improved materials for this. Okay, I'm going to show you one more example because it has this cool picture in it, and then I'll sort of start to wind down a bit. You can do interesting things when you get a lot of data. And this is new to us because material scientists usually never had a lot of data. You know, data is painstakingly derived in the lab, one piece at a time. And it's not like computer scientists or cosmologists, right, who look at the stars and have like a terabyte of data. We rarely have a lot of data. But once you start computing, you get a lot of data. And this is an interesting map. This is the periodic table on one axis and the periodic table on the other one, all the elements, right? And what this tells you is how easily two elements substitute for each other, retaining the crystal structure. So if the element here is like, if this square is light, that means those two elements substitute easily for each other. And we don't put chemistry in this, right? We just sort of like get structured data. We don't put the periodic table in here. We just do math on it. And chemistry comes out, which is kind of cool. You know that like blob of white stuff on the bottom? That's actually the rare earths. And we know that the rare earths all substitute really well for each other in crystal structures. The sort of more central white, where it's lighter than in the rest, this is the transition metals, which we all know substitute reasonably well for each other. Not always, but reasonably well for each other. So now you can do design with this, right? We can take existing compounds and start modifying them because we know what we'll substitute in there. And so to make a long story short, we did that on battery compounds. We started off with the idea we need phosphate groups for safety because phosphate locks up the oxygen. And we wanted vanadium, and because vanadium is what's called a double redox couple. It has 2 electrons it can exchange, so you can get more battery capacity. So we basically told the computer, take all known compounds and see which ones you can easily make into phosphate compounds or vanadium compounds, or actually both. And it came up with this compound. This is actually a compound the computer came up with. I wouldn't be able to like write this down, you know, P207 3 times, P04 2 times. This was actually invented by the computer, and the student who came up with it, or who read the computer file, I should say, was so excited about this that he said, you know, he was a theorist. He said, I'm going to make it in the lab myself. So we got him a lab coat. We got him some training. You know, he just did standard powder firing, and it came out. This was made within a week. We don't always have that much luck. You know, sometimes we struggle for months and months. So within a week, sort of this novel compound was made, a battery compound. Its charge and discharge is pretty much as predicted. And it's a good compound. It's not the best battery compound out there, but sort of an example of something that, you know, a novel battery cathode that the computer sort of largely designed by itself. Okay. So let me come back now sort of full circle on the materials project. We sort of put all this data online for people to work with in the materials project. And so what's the reaction of the community been? The materials project started online in 2011. Late 2011, and so today we actually got a grant from DOE, which started about a year later. We actually have almost 5,000 users. This slide is a bit old. Actually, a lot of companies register to use it. We don't track what people do. This is like a one-issue companies always have. So we have a privacy policy like everybody else. So about a quarter of our users is actually out of industry. You know, some examples, most companies do things with it and they don't tell us, and that's fine with us, right? It's an open source thing. Once in a while, they share things with us. This is something Intermolecular shared with us that they did. They actually used the materials project to look at high-K dielectric interfaces and reactivity between different layers, and have used that actually quite extensively. They actually have used it on another project There has been a lot of data in the Materials Project on photocatalyst materials, so things for water splitting. And these are materials typically you want to reduce the band gap of known photocatalysts, which are mainly oxides. You want to reduce the band gap so you can absorb more light. And we put a bunch of predictions in there for oxynitrides. And Intermolecular has actually made some of them. And the bottom graph is of the agreement of band gap between the theory and the experiments, which came out quite nicely. My own company, startup Pelion, uses this extensively. Pelion was founded a few years ago and works on magnesium batteries. This is sort of the equivalent or the next step from lithium-ion batteries. What we work in lithium-ion, you move a 1+ ion around, so you kind of move essentially 1 charge per mass unit. With magnesium, you would move 2 ions around, so at least in principle you can double the volumetric and gravimetric capacity, but it's actually better, and the reason is that in lithium-ion, you cannot use a metallic lithium anode because it's too dangerous. It tends to form dendrites when you replate the lithium. In magnesium, you actually can use a magnesium metal anode. And so you have an extremely energy-dense anode. And here's like a comparison slide. If you take a picture of a commercial lithium-ion battery and you take the thickness of the anode layer and the cathode layer, and you make the same comparative thickness on a magnesium battery, you see that you end up with much thinner layers. So this is mainly a technology for extreme high volumetric energy density. And volumetric energy density is important, right? Everybody talks about weight of batteries, but the game is really volume, right? Weight, secondary. Volume, you know, I don't have my phone with you. Your iPhone or your Samsung phone is the most expensive real estate on the planet, right? That thing costs $600-700. If you can make, you know, if you can make a battery with higher volumetric energy density, they give you a fixed volume to put the battery in. And if you have better volumetric energy density, you have more energy in your battery, right? They're not going to give you more volume because they need volume for the electronics, they need volume for the display and all that kind of stuff. So volumetric energy density is really, really what the game is. And I would even argue that all the way up to cars, volumetric is much more the game than specific energy, which is why we're so excited about this kind of technology. It is also being studied now by J. Ceder.
I'm sorry, I cannot read. Is that 1400 m/hour on the
Yes, so that's actually per liter, right? And then they're plotted so as to give the same total capacity. Okay, so I mean, just some slide that doesn't really mean much, but Pelion sort of uses computation to screen through enormous amounts of materials for cathodes because this is a new field. Very few people have actually done this, so there's very little out there to actually existing knowledge. So computation was actually extremely important to work through this to, you know, when you're a small startup, you can't put 500 people on trying to find new materials. You really have only a few shots at it. So pre-screening with computation was actually very important. So let me sort of summarize. I want to make sure we have enough time for questions or debate. I do think that, you know, materials science and materials design has been a bit of a stepchild in the sciences, right? It's been a tough field to do innovation in. It's been a long field, right? Everybody always asks us about, oh, you don't have a Moore's law, blah, 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 right? You know, materials is just hard. It's a hard field to come up with new things and new things that make it all the way to commercialization. I do believe strongly that that will change. I think we, you know, 10 years from now, I think that if you're a material scientist, you will live in a world where all your basic information will be known. And it's going to be about what you do with it. And I always make a bit the comparison with the internet, right? Again, if 20 years ago, right, it was about, did you know the birthplace of George Washington? Did you know when he was born, right? All this sort of factual information. Today, we don't consider that important anymore, right? Because you can get all the facts online. But it's what you do with it that is becoming much more important with that data. And I think we're going to see that in material science as well. We're going to see that shift from sort of data gathering as an important step, right? Because, you know, one phase diagram was one PhD thesis 10 years ago. You took 3 elements, right, and you wanted to know how they behave in any composition temperature. That was one full PhD thesis. That's like, you know, a day or 2 on a computer these days, right? So it's going to be much more today or in the future about what you do with all this kind of information. So So I think you should start thinking like properties on demand, maybe similar to what we do with the internet today with facts on demand. So, so please join us, and maybe Tony Stark was right after all. So, thank you.
Professor Ceder, thank you. I just wanted to, I guess, make my own comment, which is that as a materials scientist undergrad, this makes my undergrad look very, very easy, but it was not. So I would have liked to have had a Google, I guess, from my undergrad. We'll move over to questions now, but I wanted to start off actually with one from one of our registered participants. And they were asking, and you can kind of understand that the Bay Area is big into solar too. And that is, what are kind of appropriate battery, materials and batteries out there for, renewable energy generation sources, such as solar and wind and different size capacities too?
Well, there's so many aspects of that, right? The whole piece, let me start with the piece that's hard to do, right? The piece of load leveling, sort of if you want to move electricity, say, from night to day, right, the very rough load leveling, that's hard to do, right, because your price point has to be really low. But you don't necessarily need to do that, right? So there are interesting entry points for batteries in the grid, right? Demand management, very important, right? A lot of people in California pay demand charges, right? So demand charge is you pay for your peak power, essentially, right? You pay, if you go over a certain amount, even if you don't only do it for 10 minutes in a month, they slam you. If you're an industrial producer, an industrial user, they slam you with a demand charge, even though you don't use that electricity at all the rest of the month. So things like frequency regulation, grid stabilization is probably where the entry points are for this kind of thing. I think it's going to be interesting to see what technology is going to be used, right? Because today we see that pretty much everything's being tried. Everything from, there are people who are putting large lithium-ion battery packs together for the grid, right? And there are people who are working on, the other extreme, which is sort of like, I would say, flow batteries. Low energy density, but with low cost potential and scalability potential. And I think it's really early to say who is going to be the winner. And my guess is that we will, for quite a while, go with all these technologies, each sort of going into their niche, right? I would never underestimate the lithium-ion industry, right? Because the lithium-ion industry today is a commodity industry, And again, this is what Tesla saw so well, right? That you can go and buy 18650 cells from a supplier in Asia, right? And it's the cheapest way to get energy storage today. Because it's a commodity, right? It's the same thing over again. It's not sort of in an academic way the cheapest technology when you look at it on paper, but it's made by the billions, right? And that's what makes it cheap. So you have to keep that in mind, that if you build a new technology, even though in principle you may be cheaper, you also got to have a pathway to be cheaper in the market. And you got to sort of make it there, right? And this is a message for all the startups, right? It's not good enough to have a technology that ultimately will be better, right? You have to have a pathway to get there and market points where you enter to get there. So, but I think we're going to see like all kinds of battery types being used in the grid, especially here in California, right? With all the regulations starting, I think it is a potentially big market.
You mentioned that there are hundreds of thousands of known compounds. You also mentioned that one new compound was discovered. Is there value, do you think, in letting loose with spare cycles just in a search for more and more compounds to fill out that catalog?
Yeah, I think there's a lot.
Like folding at home or something like that?
Yeah, no, and we've had sort of, we've had talks about, we've had conversations about that. The technical aspects of these calculations make it just a little harder to do things like, folding at home and so, because these tends to be somewhat more memory intensive, they run longer, but it's not impossible to do it in principle. It needs some people who seriously work on it. There's the software engineering on it. But yeah, we did that in a small space just for fun. We once asked the question, run through all ternary oxides, so things with two metals and oxygen, right? And I think we came up with like 300-400 new compounds. Computationally, we didn't have time to go and make them all. We put them out in the literature, and slowly people are sort of dribbling, oh, we made this, we made this, we made this. And so, yeah, and I think that will be done, basically. You will start to see these sort of searches for new compounds, rather than what we do, right? We target compounds that are good in a particular property. We do targeted searches. But I think it's only a matter of time because people just say, like, you know, let me run like all combinations of 4 elements and I have spare cycles and let's just see what comes out, right? And maybe somebody else will later figure out that it's useful for something. But it's only computing, right? I mean, computing in the end is not that expensive. Computing is mainly cost of power, right? So you should put them in Iceland.
Thank you very much. It was a great talk. And I was wondering if you have any data on the thermal characteristics of the new battery, and also the state of health after n number of charge and discharge cycle. Thank you.
Yeah. So we have some of that data. Some of it I can share. Some of it I cannot. It's still an early technology, but thermal characteristics are very good. And the reason the good comes with the bad. So magnesium is a metal that passivates very strongly. You know, magnesium, when it oxidizes, makes magnesium oxide, which is impenetrable for many things. The only thing that attacks it is chloride corrosion. And so that's actually a good thing. So as soon as magnesium sees oxygen, bam, it passivates, nothing happens. So you can look at a thermal profile of a cell like this, and basically nothing happens. If you work with an organic solvent, then you still have the same problem as the lithium battery industry, that if the solvent comes loose and sees, you know, sparks and stuff like that, you can still have issues. But the electrodes themselves are pretty much inert. So that's the good news. Yeah.
So what about charge and discharge cycle?
Charge and discharge cycles are pretty good. There's still a lot of work to be done there. So it's not quite where the lithium-ion industry is, but they are pretty good already.
So you said earlier in the talk it takes 18 years before a material gets from discovery till it actually gets used. So are you expecting 18 years before your battery material gets used?
Actually, and our battery contains many more materials, many more than one, right? No, you know, so we could have never done Pelion without computation. That I can say. Because it was such a new field, such a new technology, I think it would have been a fool's start to do it without computation. But we have done it. Actually, you can look up the patent literature. Some of it is in the patent literature already of things that work. And you know, even with computation, it's still hard. But first of all, computation is really good about telling you the things that don't work, right? And this is very important, right? If your scientist comes up with a lead, oh, I think this material will be great for, you know, magnesium intercalation, right? You do a bunch of calculations, you first show them, oh, it's the wrong voltage, forget it, right? Or it has no mobility for me, forget it. So it's extremely good at cutting dead links in your research. And that has given us very high efficiency in coming up with new materials. And I would say it's now more, the company's now more at the issue is now more at the point of system engineering, at cell engineering.
Thank you very much. Do the computations work with amorphous, glassy materials, or is it just crystalline materials?
Great question. In principle, they do, but in practice, not really kind of in a high throughput mode, you know. And the problem is both theory and experiment, right? So amorphous materials are never as well characterized, right? So that's part of the problem, right? You know, a crystal structure, you do diffraction on it, you know the structure, you know where the atoms are, so you know when you're right. And so you have an important benchmarking going on. That's a lot harder with amorphous material. So it's doable, and there are people who do it. It's not quite sort of ready for complete scalability. But there are projects on liquids. So there's part of JC's, or the Energy Storage Hub, run that's now in LBNL, where they do electrolytes. So they are doing sort of things that are more complicated, that are, you know, they don't have structure either, right? They're liquids. That are being done in this high throughput mode. So I think it will come, but you know, we are pretty pragmatic people in the end. We're going for the low hanging fruit first, right? I need a pathway to sustain this too. I can't ask DOE for 10 years of money.
So you talked about the availability of germanium, which actually can also be gotten out of certain coals. But phosphorus is actually a problem in the long run. So Actually, you want to avoid phosphorus for batteries because we need it for our bodies.
Yeah, but we have a lot of phosphorus in.
Actually, there's not as much as you think in terms of.
I think we have quite a lot of phosphorus around, though.
You should look up the data.
Switching from batteries, have you looked at characteristics of phosphors that would be used in lights?
For like emission and stuff like that?
Yeah, for emission.
We haven't. There are other people who've done this kind of stuff, but we haven't ourselves.
Who are they?
I'd have to go and look back. I've seen work in that area, right? Because, you can do it, right? You can look at the emission spectra of these kind of things. Now, phosphorus is probably the one area where high-throughput synthesis and so has had quite a lot of success too, right? Because high-throughput experiment is very good when you have a visual signal, right? If you don't have to make contact on something, it's great, right? Because that's often in high-throughput synthesis the problem, right? Like high-throughput battery work, while it's been done, is tough experimentally because you basically not just have to make a material, you have to make a battery with it, put contacts on it and stuff like that. But the phosphorus work, of course, is like actually here in Silicon Valley, right? A lot of it was done. So.
What about interfaces between two different materials that are both crystalline?
Great question. God, you guys have all you find all the weaknesses. We, random crystalline interfaces we don't do. We look at interfaces between solids and gases and liquids. That we do. And only solid when they're sort of special, like the people who do MBE growth and stuff like that, who make the super lattices, because they're controlled, right? We know exactly what we need to look at. If you say like, if you take an extreme example of like take a random grain boundary in a metal, or polycrystalline. I mean, I wouldn't even know what to compare with, right, if I do the simulation. So that's a bit farther away. And you will see, for example, right, that the impact of a lot of this sort of ab initio computational work has been much higher in optical properties, thermodynamic properties, kinetic properties, but much less in the mechanical arena. And there's a reason for that. It's just a lot harder. And mechanical properties live at so many different length scales at the same time that it's sort of much harder to do in a simulation approach. And there's smart people working on this, right? But I would say the field is probably, the field is probably where we were in our area 20 years ago. And that's not because they're stupid, right? I mean, it's just a much harder problem.
As you develop these new materials, clearly do you patent them, or do you patent the process of building them? And if everybody's
patent them.
So everybody's got their secret formula for a battery, and so if, say, Apple comes out with a battery, what's the regulatory process for, how do you know if it's safe and all this?
Well, I mean, first, so in many cases our sponsors are corporations, right? So the open source is funded by DOE, but a lot of the original work was sponsored by companies. We wouldn't have been able to do it, and any standard MIT research contract gives them rights of first refusal. So the way MIT operates, like many universities, right, is that they own the rights, but the company has right of first refusal. So, and they can tell us to patent it, right, before publishing, which is what usually happens if it's important. So you can find all of them in the patent literature. It's not like they're that secret. You could find them in the patent literature typically, right? And if they don't take their rights, then they go to the broader community. What we do in research contracts, though, is that companies own the right of first refusal to the invention, but not to the data, right? And this is an important distinction. So once it's sort of gotten the materials innovation out of it, the data can go online. It's like, you can't patent the boiling point of water, right? But you can patent the machine to boil in a new machine, right? I mean, right?
I think we're going to take one more question and then
I think
follow up.
Gentleman here has raised his hand for a long time. So and I think he's the president, right, of the club? So I think you're going to owe him that one.
So back on liquids, amorphous systems, and so on, have you used this to predict solubility parameters and basically improve a relatively challenging field?
So solubility in liquids, is that what you mean?
Yeah, basically, as you're looking at solubility or how to dissolve or what systems will be suitable for dissolution of various materials, solubility parameter estimations and so on is fairly challenging.
That's in part what the Pourbet app does if you go online. So it may not give it in exactly the form you want it, but that's the data that sort of builds that app. It essentially looks at materials and whether they dissolve in water or even which component dissolves. You may have a multi-component system and only one element may dissolve, for example, leach out. That's like exactly what that app does.
Thank you.
I think you need to come to your president.
So I'm trying to understand what your computing power does. You talked about a germanium compound that someone produced, and you were able to make ion substitutions in that and predict properties of the various products that would be formed. And you also talked about a student who came up with a vanadium product sort of de novo, and just simply saying, these are what we want to put in it, what sort of properties do we get? Could you have used your system to generate the germanium product initially, given the right parameters that you put in?
Yes, I mean the answer to that is yes, you know, we weren't even working on that problem when that compound came out. It's hard to say, right? Could I say, would we have found it if we'd started like 5 years earlier? It's hard to say. My guess is yes, given how widely we are investigating a space. And to be honest, what we are doing now is looking for other ones, right? Because in some sense, what that paper did was, it was a proof of concept, right? Suddenly there was this like, oh my God, the conductivity can be high in these solids, right? And now, of course, we're looking for other ones, right? So maybe next year, I can tell you, yes, we would have found. Would we have found it? I think so, but it's hard to say for sure, right?
Well, Professor Ceder, thank you again.
Thank you.